All right. Hey, everybody. Today, we are going to be talking about matrices, a concept that's ubiquitous throughout higher mathematics. If you've taken a class in Calculus 3 or linear algebra or differential equations, there's a, a good chance that you've already seen this concept. However, just want to give a very quick blanket review to cover some of the important properties that we'll use going forward for matrices. So first of all, what is a matrix? A matrix is simply a grid or an array of different numbers. And specifically, when we talk about a matrix, we have to talk about its size. So a matrix of size m by n, aka an m by n matrix, is just going to be a grid that contains m rows and n columns, right? And that order is important. So the first number will be the rows, second number will be the number of columns. And therefore, there will be a total of m times n entries. Notationally, we'll usually denote matrices with an uppercase letter, like an uppercase A, or we'll use these soft brackets with the A sub ij notation. So the individual aij's are going to be the entries in the matrix. And so aij is going to be the entry in the matrix that is in the ith row and the jth column. Right, so that's how we'll denote that. Here's an example of a matrix. This is a matrix that is of size 3 by 4. Notice that it has 3 different rows, 1, 2, 3, and 4 different columns, 1, 2, 3, 4. I'm denoting it with a capital letter A and with these soft brackets. And if I wanted to describe a specific entry in the matrix, I could say, for example, the A, let's say 2, 3 entry. Well, that would be the entry that is in the second row and the third column. And we're always going to start by counting in the upper left corner and going down, right? So second row, that would be 1, 2. And third column, that would be 1, 2, 3. And so the entry A23, the entry in the second row, third column, is just going to be this number here. In this case, that's 3. So we'd say that the A23 entry of this matrix is just 3. Similarly, if we have the A11 entry, that would just be first row, first column, so that's going to be a 1. If we wanted to have the A24 entry, that would be second row, fourth column, and so that would be a 0. And, you know, if I said something like A25, that would just not exist, right? So, because there is no fifth column in this case. It's worth noting that if you have matrices of the same size, you can add them together. So if they both have the same number of rows and same number of columns, you can add them together in a process called matrix addition. And similarly, if you have a matrix and a scalar number, you can perform scalar multiplication. And this will work exactly like it did for vector addition and scalar multiplication in the vector setting. Specifically, everything will be done component-wise. So if I wanted to, for example, let's take a smaller matrix. Let's take the matrix just 1, 2, 3, 4, and add that to a matrix of the same size. Let's say 0, 0, 3, 8. I would add this component-wise. So the same components would be added together. So we'd get 1 plus 0. We'd get 2 plus 0. We'd get 3 plus 3. And we'd get 4 plus 8. Right? So that addition would be done component-wise. All right. Unlike vectors, we also have an idea of matrix multiplication, right? So remember, we had to dance around the idea of vector multiplication a little bit. With matrices, we can multiply matrices together if they are of the appropriate size. And it's going to be a little bit tricky. So if we have 2 different matrices, A and B, these matrices will have potentially different number of rows, different number of columns, and we can multiply them together if a certain condition is satisfied. So our matrix A, let's call that an m by n matrix, right? And again, that means that it has m rows and n columns. And matrix B, that could be some other size. So let's call that a p by q matrix. So p rows, q columns. these two matrices can be multiplied together if the number n is equal to the number p, right? And sort of said in plainer language, it's if the number of columns of the first matrix is equal to the number of rows of the second matrix. And if that's true, right, if n is equal to p, the result will be a matrix of size m by q. Right, so it will be a matrix with m rows and q columns. Right, so already a little bit tricky. We could be multiplying matrices of different sizes together. As long as this condition is satisfied, the result will be a new matrix, possibly of a different size. Let's see an example. Right, so here's an example. We've set up two matrices, and we can do a quick check to see if we even can multiply these together. Right, so this matrix here, this is a 2 by 3. It has 2 rows, 3 columns. This matrix is a 3 by 2. It has 3 rows and 2 columns. And we just check and confirm that this number here, number of columns of the first one, is equal to the number of rows of the second one. And they are, check, check. Now the result, in this case, will be a 2 by 2 matrix. So we'll get a new matrix that's 2 by 2 as a result. Right? And the way that we multiply this together is going to be completely mechanical. We're going to do this as follows. Right? If this is a 2 by 2 matrix, it'll have these 4 entries in it. We're going to take for the first entry, the upper left entry, I'm going to take the upper row of this matrix and the left column of this matrix, treat them as vectors, and perform a dot product computation. Right? So treating these as two separate vectors, I could have 1, 2, 3 and 2, 4, 0. And when I take the dot product of those, I would get 1 times 2 plus 2 times 4 plus 3 times 0. All right, and so that written out, we get 1 times 2, so that's 2, plus 2 times 4, that's 8, plus 3 times 0, and that's 0. And so this upper left entry becomes 2 plus 8 plus 0, and that ends up being 10. Right? We'll do the same thing to compute each of these other entries, and that's how we'll get all 4 of our entries. So the upper right entry will be comprised of the dot product of the upper row and the rightmost column. So that's going to be 1 times 1 plus 2 times 2 plus 3 times 1, right, or 8. The lower left will be this lower row and this leftmost column. So lower left becomes 7 times 2 plus 4 times 0 plus 1 times 0. So that's 14 plus 0 plus 0. And finally, the lower right, that will become 7 times 1 plus 0 times 2 plus 1 times 1. That's 7 plus 1. And so the end result, right, scooch over here a little bit, the end result will end up being a 2 by 2 matrix with the entries 10, 8, 14, and 8 again. And we've successfully multiplied our 2 matrices together to get a new matrix, possibly of a different size. Okay, so if you've never seen that before, with a little bit of practice, you'll be doing this like a pro, and especially, like we said, matrices and this sort of matrix multiplication becomes very, very pervasive throughout higher mathematics. So we see this a lot. All right, worth saying out loud, matrix multiplication defined this way is confusing, but it does have some nice properties that we might expect from multiplication. And so here are a few of those nice properties. First is that the property of multiplication is associative. And what I mean by that is that if I have three matrices, A, B, and C, that I want to multiply together, it doesn't actually matter which order I do that in. So if I take A times B and I multiply that by C, right? A, B, and C are matrices. This is the same as if I had done first B times C and then multiplied by A, right? So if I were to just write the expression A times B times C, that is unambiguous, right? I can determine what that product is without worrying about the parentheses. This property is called associative, right? So multiplication is associative. Additionally, multiplication distributes across addition. And what I mean by that is if I, again, have three matrices of the appropriate size, A, B, and C, then if I perform a computation like this, right? And again, this would mean, order of operations, that I'm adding these two matrices together, and then whatever that result is, I'm multiplying A times that. Well, this is exactly the same as if I had A times B plus A times C, right? So matrix multiplication distributes across addition, right? And this is a nice property that we might hope any sort of multiplication has. However, there are some not so nice properties of matrix multiplication, things that we might want multiplication to achieve, but that is not achieved in the case of matrix multiplication. And one major one, right, one huge one, is going to be that, in fact, if we have two matrices A and B, the order in which we multiply them actually matters considerably. So it is not necessarily the case, in fact, it will most likely not be the case that A times B equals B times A. It is most likely the case that this is not true. Right? And this can be seen very quickly if you just think about the size of matrices that we would get when we multiply them. Going back an example, right? This example here, when I multiplied these matrices in this order, the result was a 2 by 2 matrix. What should the size of the resulting matrix be if I were to flip the order? Well, if we flipped the order, it turns out that this would be a 3 by 3 matrix that we would get as a result. And so clearly, A times B, in this case, was not equal to B times A. So that's a really interesting sort of warning that matrices will often not behave, or matrix multiplication will not behave the way we might expect multiplication to behave. For example, multiplication of real numbers. So these will come up from time to time throughout our semester. They'll come up more often than not as the semester progresses, and we'll see matrices in many other classes besides this one. So thanks very much. See you next time.